Welcome to another talk hosted by EERI New England. My name is Isan Kianirad and currently serve as the president of the New England chapter. Before jumping to the presentation, I would like to use this opportunity to invite you to get involved with the chapter, particularly if you have any idea or you would like to volunteer and help. Please reach out to me or other board members. We always welcome any suggestions or additional help. With that, I'm thrilled to introduce our speakers today. Dr. Seda Gautier-Erbis is a project engineer and assistant project manager for Geocomp Corporation in Massachusetts Consulting Group. She has been with Geocomp for 6 years, holding a doctoral degree in geotechnical earthquake engineering. She has been leading the project management and technical efforts for one of Geocomp's largest consulting projects on seismic assessment of coal ash impoundments. She has over 7 years of experience in geotechnical earthquake engineering, especially in advanced laboratory testing. She has authored and co-authored several publications in peer-reviewed ASC and ASTM journals and conference proceedings. The other speaker is Mr. Ryan Lavarotti, is a project engineer at Geocomp as well. He is responsible for a range of project activities, including geotechnical design, laboratory testing, data management, computer-based modeling, field investigation, and project management. He has been involved with different aspects of engineering work, from litigation review to design analysis to information research. He has extensive modeling experience in a variety of geostructural software, including GeoStudio, Rock Science, Deep Soil, and FLAG. With that, Seda, Ryan, it's yours.
Yeah, let me just do a brief. Ryan is going to start with his part of the slides, and I will take over somewhere in the middle where we switch to the seismic assessments, and we'll be covering quite a bit of stuff here. So again, and thanks for having us, and I hope you all enjoyed the content that we're about to share today. With that, I'll leave the floor to Ryan.
Good afternoon. As mentioned, I'm Ryan Lavarotti, and the topic for today's presentation is the determination of the undrained strength for contractive coal combustion residuals, CCR, for seismic slope stability assessments. A brief outline of this presentation will be to give an explanation of slope stability as well as its consequences. We will then go into the description of what coal combustion residuals are and what tools we use to evaluate them. We will then show how these tools and analyses are used to develop site-specific assessments of CCR impoundments. We will want to give you a learning outcome that there is a lot of uncertainty and variability in strength and stiffness parameters for CCR materials, and this requires the need for site-specific seismic assessments for slope stability containing them. So the first thing to start off with is what is a general definition for slope stability. Slope stability is the investigation and evaluation of soil slopes, whether they're natural, embankments, or excavations, comparing the shear stress with the shear strength along a potential slip surface. As shown in the diagram on the left, we have a slip surface in the form of a circular arc going through the soil mass. The factor of safety for a slip surface is the ratio of the shear strength of the soil divided by the shear stress required for equilibrium. So when we're talking about slope stability, especially with the factor of safety, there are several factors that can affect the factor of safety. First is there is a decrease in the shear strength, and the next is there is an increase in the shear stress. An example of factors affecting the decrease in shear strength include an increase in bore pressure, strain softening, and even creep. An example of increase in shear stress includes surcharging, excavation at the base, or an increase in water content. Focus of this presentation is earthquake shaking, the increase in shear stress in the soil, and the post-earthquake condition, a decrease in shear strength. So for slope stability, There are two general mechanisms that will trigger shear strength. There is the contractive response and the dilative response. In the context of this presentation, the samples are considered to be shearing undrained. Earthquake loading and post-earthquake loading conditions may trigger a contractive response based off of the material state. Typically, contractive responses produce a lower strength than the dilative response. If overlooked, it can produce an unrealistic, favorable stability assessment, leading to a potential failure. An example of the contractive strength is shown by the red line in the diagram on the left, and the dilative strengths are shown by the blue lines. So what are some slope stability problems where slope stability has shown to be a problem? The best example for this is shown through the case histories. A couple of case histories involve the St. Francis Dam, the Vaillant Dam, the Rissa landslide, and the New Orleans eye wall failures. So each of these failures have had deaths ranging from as low as 1 to as high as 2,500. Towns downstream of these dams had, in many cases, been destroyed. Farmlands were ruined in these situations. Millions and billions of dollars wasted, or not wasted, but spent. So the St. Francis Dam is shown on the left. Water had blown out after the dam had failed. Roughly around 400 people had died in that situation, possibly more given the unknown number of immigrants downstream. The Vaillant Dam had failed in the sense that a landslide behind the dam had occurred, triggering water to flow over the dam and destroying several towns and killing up to about 2,500 people. The Rissa landslide, as shown in the top left, destroyed many farmlands, a lot of farmland, as well as the neighboring town on the other side of the river. And the New Orleans eye wall failures resulted in about 80% of the city being underwater, killing several dozen people and damaging as many homes. So in these situations, this is just with soil and water. So now what happens when you add CCR? It doesn't get too much better after that. Coal combustion residuals are particulate materials produced from burning coal from a coal power plant. These include fly ash, bottom ash, slags, chemical byproducts such as gypsum. Generally speaking, these are all fine-grained materials and are easily absorbed into living tissues. Pollutants like mercury, cadmium, and arsenic are also found in these byproducts, and these are poisonous to living tissues. Furthermore, these contaminants are not that easy to remove from the environment and often require over-excavation to make sure that you've removed all the materials from the area. So coal combustion residuals are generally placed into their trash barrel of a home after they've been produced by a variety of means, and they vary based off of where you are, what equipment that the plant has, and what equipment the plant has. But generally speaking, this can be covered in two great basic topics: sluicing and stacking. Stacking is usually dry stacked CCR material and compacted, mostly unsaturated. Whereas sluicing is a loosely placed hydraulic CCR with no compaction, very loose and saturated. These CCR, whether it's a stack or a pond, is usually encompassed with a dam surrounding it. So a couple examples of CCR failing is shown through a couple of case histories. The first one is the Buffalo Creek failure in Virginia. In 1972, it was a sudden failure. There was no warning. Approximately 14-meter high embankment of coal waste that was built on coal refuse, and it was built using the coal wash tailings for the coal main. Everything they had burned at the facility had been generally stored upriver. The collapse of the dam was by slumping and sliding of the downstream after a heavy rainfall. In essence, the water was flowing through the dam, which helped it push it down the stream. Roughly 500,000 cubic meters had spilled from this dam failure. The tailings then, these CCR materials then traveled 27 kilometers downstream at roughly 2 meters per second. It killed over 100 people, injured over 1,000 more, destroyed 500 plus homes, and produced property damage and highway damage in the order of $65 million. In today's money from 1972, that's well over $1 billion. Another more recent example is the Kingston failure in Tennessee. This occurred in 2008. It was sudden, there were no warnings, and it was suspected the day before. Roughly, this dam was about 30 meters tall using an upstream dam embankment for the coal ash for the power plant. It was a contractive failure through a thin, weak foundation layer leading to liquefaction of the stored ash, followed by a mud flow. This mud flow released 4.1 cubic meters of liquefied ash flowing 7 kilometers down Emory and Clinch rivers. Over 180 properties were damaged, and $1.2 billion was paid out by TVA to clean up damages. So now that I possibly have scared some of you into what CCR can do, what tools do we use to evaluate its properties? On the left, we have an example of bottom ash. It's got the consistency of a silty sand in many cases, in some cases a pure sand, depending on how it was burned at the facility, whereas fly ash will generally behave with the consistency of mud mixed with Play-Doh, if any of you have played with Play-Doh. Also, fly ash has a tendency to be very wet when sluiced, as is shown in the picture here. So CCR materials tend to have a specific gravity as low as 2. This is a byproduct of CCR materials being burnt, the coal remnants of dead, if you want to call it dead dinosaurs, if you will. Bottom ash, as I mentioned earlier, tends to be classified as silty sand, as shown in the diagram below, whereas fly ash has a tendency to be classified as silt, as shown in the diagram below, with a very high fines content in the order of 95 plus. CCR materials have also a tendency to be non-plastic, but in instances there are very low plasticity if it does occur. In most cases it's no, but there are some instances where it shows very little. Another unique feature of CCR materials is that they can have water contents as low as 20% when compacted or stacked, or as high as 80% when loosely sluiced. When it is loosely sluiced, the wet non-plastic and loose CCR will contract and be susceptible to liquefaction. So on this image, the other issue that comes up is the ash in the CCR ponds tends to be variable, very variable. They exhibit considerable variability as they are poured or stacked into the deposit. As shown in the X-rays on the right, the first X-ray shows distinct horizontal layering, as can be seen here, here, and here. The phenomena that usually happens when this happens is the darker lines represent coarser CCR that settled out after sluicing was ongoing. So you might get layers of coarse CCR followed by layers of fly ash. Think of it as a hydrometer test when you're doing sieve analyses. And in some instances, you may not even observe the layering that is shown in this X-ray of a tube, as is shown in the other two tubes. So how do we evaluate the seismic stability of CCR impoundments? Well, we start with a general approach. First, we start with our site investigation. Then we work on developing our initial round of parameter development, which is to determine our peak strengths and our stiffness parameters, which will in turn be used for our 2D dynamic response for finite element analyses, which will in turn be used to develop our pseudostatic stability analyses, which will then be both of those, the dynamic response and the pseudostatic response, be used to develop our second round of parameter development to develop our post-earthquake strength parameters. Did it liquefy? Did it lose strength? And then following that parameter development, we will then go into the post-limit equilibrium for post-earthquake stability analysis. So to start it off, we do our site investigation. Site investigation includes a combination of field testing and lab testing. Field testing includes collecting disturbed and undisturbed samples, geophysical tests, and geotechnical profiling. Laboratory testing, after samples have been collected from the field, are used for developing X-rays, index tests, strength tests, dynamic tests, and cyclic tests. So in order to get our samples, first we need to do some drilling. For liquefaction purposes, it's recommended that mud rotary drilling be used. The drilling mud needs to be maintained at the top of the borehole at all times during drilling operations. The drilling mud is used to help create a surcharge at the bottom of the hole to help represent what was lost from the hole as you're drilling down, as well as to maintain a gradient on the surcharge on the bottom to prevent uplift into the borehole. So once we start drilling down into our borehole, we can start collecting what's known as split spoon samples. Split spoon samples, along with SPTN values, provide an in situ index for the soil, as well as a disturbed sample to test. In addition to split spoon sampling, there is thin wall tube sampling. Thin wall tube provides an undisturbed sample for an advanced test, such as a DSS or a resonant column, which we'll get into a little bit later. And once you're done with sampling from your borehole or have reached your target depth, you can then use that borehole to install an instrument, such as a piezometer. Piezometers can be used to help develop pore pressure profiles for your cross section. In addition to cone penetration test, in addition to the field work is cone penetration testing. This provides a continuous profile of data, especially shown in the tip resistance profile, which is shown as the first column, and the sleeve resistance profile in the second column. Additional modules can be added to the cone penetration test, such as a pore pressure sensor, as shown in the third column. The third column, as well as a stiffness geophone to measure stiffness, as shown in the fourth column through the shear wave measurements. Important note to add here is that the CPT data provides an index to strength, and that the data needs to be correlated or calibrated to apply a data strength profile along its profile. In addition to cone penetration testing, there is also cross-hole seismic testing. This provides a profile of the input parameter for dynamic response analyses, namely shear wave and compression wave measurements. This complements the CPTU data, which is a downhole measurement, compared to the CPT measurement, which is from the ground surface down to your point. So after we've collected our field samples, then we bring them into the lab. Disturbed samples will usually undergo index testing, such as grain size, Atterberg limits, classification, specific gravity, water content. In addition to those, we will take our samples from our thin wall samples and run them under our more advanced tests. The first advanced test is the direct simple shear test. It is an undrained test under constant volume. The shearing in the direct simple shear, also known as DSS, is closer to the mode of shearing for global stability. The sample size, 1 inch, is much smaller than that of a triaxial sample, and you can get much more tests out of a Shansep test, out of a DSS test. During the test, the duration of the test is relatively shorter compared to other tests like triaxial, because the sample size is smaller compared to that of a triaxial. In addition to direct simple shear tests, we also perform cyclic simple shear tests. For cyclic simple shear tests, we prescribe a CSR from our amplification analyses, and we hold that constant. We allow the sample to cycle a certain number of cycles and let it strain and build up pore pressure as it moves through those cycles. After the cyclic phase is done, we then allow the sample to do what's called a post-cyclic shear. This is essentially the same as a direct simple shear test, only that now it's starting at the conditions after it has cycled. So in this case, it will start at a shear strain when the previous cycling had finished, and a pore pressure where the cyclic phase had finished. The next test that we do, next advanced test that we do is the resonant column test, which measures soil stiffness parameters. This is a key input for dynamic site response analyses, as it provides the small strain shear modulus, which is represented by the flat portion on top of the test. and the shear modulus reduction curve, which is represented by the curvature and the slope moving after the peak, the plateau up here. It also provides the damping curves that are, it also provides the damping curves. So after we do our field testing and our laboratory testing, we then move on to parameter development, the first round of parameter development. This provides us our peak strengths and our determination of residual and reduced strengths. So going back to our flow chart, we're going into the first round of parameter development. So the first step is to determine, is the sample contractive or is it dilative? It's common for stability analyses to use long-term conditions like your friction angle and your cohesion. This is shown by the blue line on the right going from point O to point B. Contractive materials tend to produce strengths that are lower than both C and phi, the stress path OA from the diagram, and contractive materials should use their contractive strengths, as shown by the red line. Dilative materials produce strengths greater than phi and C from the OC stress path, the darker blue line. Dilative materials should use their drain strengths, as negative pore pressure buildup during those tests cannot be fully relied upon. To give you a sense of what strengths we're looking at, the tangent of the friction angle from, say, point B can be on the order of magnitude of 0.5 to maybe 0.65. The strength, the undrained strength ratio developed at point A can be on the order of 0.1 to about 0.3, which is anywhere between half to a fifth of what a friction angle can produce. So in addition to determining the contractive and dilative behavior, you need to figure out where it is relative to its failure condition. So to figure out this, we used what's known, the CCR materials use what is known as the state parameter. The state parameter is the difference between the initial void ratio and the void ratio at the critical state condition. State parameter can be measured from undisturbed samples or from CPT correlations. As a general rule of thumb, from Robertson, if a state parameter is greater than or equal to 0, it's contractive. If it's less than or equal to negative 0.05, it's dilative. There is a condition where if it's in between, it's recommended you do further analysis or further study to figure out, is it contractive or is it dilative? As can be seen on the graph, when phi is on the positive side, if you will, it's contractive. When it's much less than negative 0.05, it's on the dilative side. So once we figure out if it's contractive or dilative, we subdivide it into zones of those contractive or dilative behaviors. We then have to figure out what the contractive strength of the CCR is. And the contractive strength of the CCR is variable. And lab testing is suggested to supplement correlations. The chart on the right shows back-calculated contractive strengths from previous failures, in addition to measured values we had taken. The gray dots represent the back-calculated values, and then the color-coded points represent actual measured values from, in some cases, different sites and with samples within the same site. As can be seen in the graph, some data points are close together. Other data points suggest a lot of variability. So once we pick our contractive strength that we want to use in our further amplification analysis, we then have to run cyclic testing on materials after when we're done it. So just to give you a reminder, this gray line represents the static test that we had previously performed. This peak point up here represents that peak contractive strength that is used in our pseudostatic and amplification analyses. Once we do finish those amplification analyses, we then need to perform our cyclic test and determine if liquefaction occurs. The cyclic test is using the CSR from our amplification analysis, and then it is applied over a given number of cycles. When we're done with the cyclic response, we then go into the post-cyclic response to determine if a reduced strength is apparent. This is shown by a noticeable difference here between the monotonic peak response and the post-cyclic peak response. It went down from about 0.21 to about 0.16 in this instance. So now we're going to go into seismic stability assessments, in which case Seda will take over.
Thank you for sending that. For some reason, the bottom bar didn't show up for me to unmute myself. Thanks for the help. Hi, so sorry about the abruption there. So now I'm going to continue where Ryan left, which is kind of the site response analysis that we do with these input parameters, with the strengths and the soil stiffnesses. And I can walk you through again from this analysis chart that we develop our parameters, and once we know the peak strengths, and once we get an idea about the stiffness parameters of these CCR materials, we perform a 2D dynamic response analysis for that. And we use this analysis results to figure out what the stress ratios are going to be experienced by the profile. And we apply those together with an application of some displacement compatible sliding block analysis to continue with our pseudostatic limited equilibrium analysis. And eventually we will be looking at some post-earthquake contractive strengths too. I want to start with giving you what it is, the dynamic response analysis we do. Given the time limitations, I'm going to be keeping it brief, but if any questions, we can get more in details of this analysis. And what you see is a typical cross-section showing some ash materials contained, and it's basically a slope that we would be analyzing, and which is on the top side. The gray zone is representing the ash. What we do here is we do a finite amount with our seismic consultants. We do a seismic, we do a dynamic response analysis to figure out how this 2D geometry is going to respond to the rock motions if experienced in an earthquake. And this finite element mesh you're seeing for exactly the same cross section that you're seeing on the top. This response is going to be really determined by two key inputs that I kind of put here as a highlighter is the ground motions that you select, and also the stiffness materials that you select for these materials. And in this particular example, the ash kind of is most part of the geometry, which is going to affect the response. And we will go into the details of how to determine those inputs. And then the results on the other side is cyclic stress ratios, basically the shear stress that is normalized to an effective stress in a soil's case. We can kind of simplify it as the earthquake shaking, or the level of the earthquake loading here is going to be computed by this response analysis and will be used in our cyclic simple shear testing to be site-specifically analyzing if liquefaction occurs, and if it does, is there any strength loss? So one of the key inputs is the input ground motions. And what we do is, as part of the site-specific analysis, that we determine rock motions that are representative of the area. And these are rock motions, and we go with 7 motions here. And what to pay attention for these is these motions have mean magnitudes representing the site, if available. And if there are synthetic time histories available, can use them for the site location to be representing the site properly. And the reason for selecting multiple ground motions is to cover the various frequency contents here as part of the response. And eventually these ground motions will get to be scaled to a USGS hazard spectrum which is unique or specific to the location of the project. And what you see on the left is basically a scaled response spectrums of each ground motions that was selected and fitted spectrally matched to a USGS hazard spectrum of the site. Another important input of this part, basically this rock motion is selected and the 7 motions will be fed into the analyses. And what you're looking for is the response of this critical slope that you're interested in. And that's what the response analysis is going to give us, that how is this motion going to be amplified or de-amplified? How this 2D geometry is going to respond to this rock motion, and determine that soil's response or the critical masses. We can call this yellow zone as a critical soil mass. And how is it going to respond, and what are the accelerations that are going to be felt by this mass? And what affects this, aside from the rock motions, is the stiffness parameters. And one of them is the small strain shear modulus Gmax, or the shear modulus reduction curves, so-called backbone curves is some quick way of calling them, in the damping curves. And what you see on the left to right side, you've also seen it previously with the sample resonant column test results, that this is the shear modulus, reducing with the increasing shear strain. This is a schematic of showing how the reduction is typically observed, and the damping increasing with the shear strain. But there are very good empirical models to include, to kind of cover for this reduction with strain changes, and what typically very available for soils, and very, very much used for the stability of the models. It is preferred to use empirical models, which are already embedded in the finite element analysis. When it comes to the CCR, though, we're trying to be cautious of how they're going to behave, and we're similar approach that we take in the other parameters, that we combine the laboratory test with some empirical relationships. So, since for the sake of finite element analysis, it'll be healthier to use the empirical relationships, we tend to keep them but modify them for ash materials. And they seem to be for these empirical models are doing a very good job for the soils like sands or clays, especially clays. But for the ash case, what we do is we look at the lab data, and what you see as data points, as lab data from different sections here, in this case from a same site. And what we do is we modify these relationships to fit to the lab data in order to represent some site-specific conditions. And we seem to find our Daily model working very well for the fine-grained CCR, and Menck model for the coarser CCRs. Once the response analysis is completed with the inputs of the input ground motions and the soil stiffness parameters, we have computed the accelerations and the shear stresses experienced by the profile. But we would like to conduct a limited equilibrium analysis. And what we do here is to use the Newmark sliding block analysis as a tool, so that we don't have to assume this sliding mass we can see an example of that here. This sliding mass is not a rigid body, and it has some displacement is allowed for it to be, and can be still called safe. So this typical, let's say this critical, the blue shade is our critical soil mass here, where we see the response of this critical mass at the centroid of the mass is a record, one of the records, of course. There will be 7 of these. Here shown as a horizontal equivalent acceleration chart at the bottom. And the Newmark sliding block analysis can produce a displacement versus yield accelerations chart for us, like you see on the right. So the yield acceleration here is the pseudo acceleration where it causes this blue mass to move. Once it's exceeded, it's going to start moving. And so that's kind of a threshold where you start cumulatively calculating your displacement if it is passed. So I'm going to try to help reading this chart. Basically, if you have a yield acceleration of 0.042 here in this case, which is the yellow line, you would then look at the exceeding points and calculate your displacements. And that would be roughly corresponding to 6 inch in this case. But if you had a lower AY, if you had a lower yield acceleration that causes the movement of the sliding block, then there would be more displacements to be calculated as more peaks are exceeding in this response motion. And that would be represented by the red and corresponding to an 18 inch. So depending on what you want to allow, what level of displacements that you want to allow in this analysis, you can select a yield acceleration that corresponds to that, which this becomes a displacement compatible pseudostatic coefficient for our stability analysis. So we basically, instead of using a yield without allowing any single displacement, we use this coefficient as a compatible pseudostatic coefficient to conduct our limit equilibrium analysis, which is then a simple limit equilibrium analysis that Ryan kind of mentioned in the beginning, looking at the factor of safety against sliding under that pseudostatic force. And we would be using peak contractive strengths for this type of analysis, which is the one that we just discussed. But not only that is the during shaking condition that we're trying to combine the efforts from finite element and the limit equilibrium. Now, we also need to look at if the material is going to liquefy and the post-earthquake contractive strengths are going to be triggered. So for that, I will be showing the same slide just to remind you what we look at from the lab side of things. We also do a triggering analysis from the field as well, which would complement this to see if the liquefaction is triggered or not. But the lab testing is the way for us to determine at least the post-cyclic strengths. So again, just to remind, this is the cyclic response of the same. We do a companion testing basically from the same tube, look at the monotonic response and then the post-cyclic response to determine these strengths. And the cyclic phase, you can see the strains that it reaches up to for this particular example. We both look at the RUs and the strain accumulation to see if the liquefaction is triggered. Even if the liquefaction, so to speak, is not triggered, by the book knowledge of it, that the pore pressure ratio was equal to 1, we still look at the post-cyclic response if any kind of reduction is happening in the strength. And in this case, this point, the peak point for the blue test will be selected for the analyses. And looking at the lab testing and the triggering analyses, we determine the zone where it is going to liquefy under this design earthquake. Why do I say design earthquake? Because the CSRs used in the strength selection will be from the site-specific amplification analysis. So we will be testing the samples under the design earthquake, simulating it under the design earthquake. And with using either residual or reduced strengths, you can see the zone is called liquefied. We would use the liquefied strengths, but conduct a limit equilibrium analysis with gravity loads only. So this is a static analysis with post strengths and look at the stability of the cross section for the post earthquake conditions. So to sum up here, the learning outcomes that we wanted to give you is the stability of the CCR CCR involving slopes can be controlled by the contractive strength. And it is really, especially under the earthquake type loading. So depending on the loading type, these contractive so-called undrained strengths can be triggered, and they can be critical for their response. But still, there is a lot of uncertainty and variability in the strength. Like as you've seen in the field to lab comparison chart, there's a lot of scatter in this data. Still, there is more room to be improved to understand, and the lab testing, specific lab testing and site-specific response analysis is warranted here to better understand the response of these cross sections and if they're critical or not. And just want to leave a note here as well. What we showed you today here are mostly CCR materials, which are coal combustion residuals, but there are a lot of tailings dams or hydraulic fill material that can be placed similarly, and some of them behave similarly, and they can be susceptible to liquefaction, and similar limitations in empirical models can apply to those as well. So some of the outcomes here is applicable for them as well. And again, the key outcome that we wanted to mention here is the need for site-specific assessments and better understanding the behavior of these CCR material. The field and the lab together investigation is playing a key role, and site-specific amplification plays a key role here. With that, I would like to thank two people. First, Ehsan for inviting us for this talk, and of course, GCOM's clients for this opportunity to work with these for these CCR materials, and our seismic consultants, Professor Steve Kramer from Washington and Pedro Ardinio from University of Washington, helping with us with the finite element analysis and selection of input ground motions and all. And of course, Geotesting Express to be able to do all these advanced testing, which is not a very easy task, and producing quality data from them. And I would like to open the floor for questions now.
Yeah, thank you very much, Seda, Ryan, to share your work and walk us through the steps required to this fascinating work. So I believe we have about like 15 minutes for question and answer. All of you should be able to unmute yourself and ask a question. So please feel free to go ahead, unmute yourself and start asking questions.
Hi, my name is Mike Pastor, and I have a question about the laboratory testing that you all do to measure your, particularly the post-earthquake strength. We all know that density or void ratio is a key aspect when it comes to post-earthquake strength. Obviously, a denser material has a much higher strength. So I'm just wondering, how confident are you that the density of your samples in the laboratory is comparable to the density of the actual material in the field?
Very good question. So we have different ways to look at that. If the project allows, we involve measuring the shear wave velocity of the samples, and just to see if the sample is representative of the field. And we also, in the sample transport, we try to monitor the vibrations that they're getting exposed to and try to avoid the vibrations that they're getting exposed to so that the sample disturbance is minimal. And during the test itself, the axial strains are controlled such that it's a constant volume test. So we don't allow the vertical displacement except going into the in-situ stresses. And that's how we kind of manage that differences between the samples and the field. And we also compare the lab testing to our CPT interpretations and see if they agree, because the CPTs are giving a better profile of the data. And if they agree well, we typically go with the field testing because it gives a better understanding of the whole profile. If there is a very much disagreement in between the two, we investigate back if there is a strong evidence to show the sample disturbance, or basically just to see if the response is unique to the soil or not. If we can't really prove that, then we go with the lab testing, showing that it is really a unique behavior.
But just the process of taking a tube sample, getting the tube out of the ground, getting a sample out of the tube in the laboratory, and then consolidating even a little bit in the laboratory, I mean, that can cause some, pretty significant densification of the sample. It only takes a little densification to have a big effect on strength. So I'm a little concerned about that, to be honest. My other question is, when you talk about using the CPT data and the correlations, those correlations are correlations to coal combustion residuals, or those are correlations to sand? I mean, I understand you have to use what you've got, but I'm only aware of correlations to sands. Is that right?
Yes. Which one are you talking about? Depends on which one. If this is the one that you're referring to, let me go back. This one.
That one.
This is based on the case histories on slope failures. Ryan, can you speak to that a little bit more deeper?
The case histories that Stark and Olson had investigated did include CCR materials and tailings.
So their curve is, well, their curve is pretty, if you want to call it a curve. I mean, so their data is the gray dots, right?
Mm-hmm.
Correct.
Right. So, yeah, I've looked at this before. First of all, I think most of it's for sand. But second of all, it turns out they draw a nice sloping line. But the best fit to that data turns out to be a horizontal line, meaning that the yield shear strength is basically, there's no correlation to CPT tip resistance. But I guess that's all you've got. So I mean,
Exactly. That's why we're kind of in between of the correlations are limited. The lab testing can do within its limits, as you mentioned. So, which we're trying to make some engineering decisions within that lab.
Okay.
Thank you very much. Yeah.
Thank you.
Any other question from audience? If not, actually, I would like to ask you one question, Sedat. You talked about the a design, ground motion selection and scaling. Would you please talk about the discussion that happens, behind the scene about if there's any discussion about importance factor and a risk category that needs to be decided, because particularly the case histories that you showed, the level of devastations, downstreams, and the casualty could be huge. So interested to know if there is any discussion about, what risk category needs to be decided and the scaling of the ground motions.
Yes, we don't include that, but that's a good point. So in this particular project, it's a seismically active area. So we were lucky to have the synthetic motions representing the area, but we didn't have enough actual records to really represent the area. So you if you want to do a frequency variability, then you have to go with other records which are representing higher magnitudes. And then scaling it down to your spectrum. It's a spectral matching. You're still disturbing the record a little bit, but as much as you can. So, but yes, that's a good point for other places. If the risk factor can be included in there, that behind the scenes there wasn't a talk about it. But I think since these things are not that simple, I guess there should be a certain logical flow to that, and that can be included in that process. especially for when the risk is relatively moderate, let's say, not that high. How do you still include it, but don't do a very conservative approach? That's a good point, actually. I'll think about that.
Any other questions from audience?
May I ask a question? This is Sunil Sharma. The graph where you had the Newmark displacements versus the yield coefficients. I'd like to know in this type of work, what is a reasonable Newmark displacement people are seeking? The second question is, you had 7 time histories, and on this log scale, the answers can be very different. Do you think using a mean of these numbers is a reasonable approach?
So the allowable displacement is one of the $1 million question that I think regulators have different takes on it. So depending on the project and what the regulations are, we follow a certain. So there is the famous 3 feet for the dams, and which doesn't really. There's all these debate about if it applies to these slopes or not. So for that, I cannot really speak to it number-wise, but depending on what the regulations that we're working against, we take our stand. We typically use this 18 inches, if not, because this 3 feet was, again, determined for the dams, and since it's not particularly for the CCR slopes, we're putting a factor of safety of 2 there to go for 18 inches to allow some displacement, but not go as far as 3 feet. So that's that. But again, that really depends on the regulatory requirements. In regards to the minimum and maximums of this, yes. So we do, again, regulatory purposes, we kind of have to report a factor of safety, let's say, then we go for the mean. But we do a sensitivity analysis to see what happens with this yield and what happens in that, and we supply a chart of that sensitivity depending on the client's needs. But that's what we typically also do, which is part of the sensitivity analysis.
Thank you.
Thanks. And I think Juan, you have a question. Please go ahead.
Yes, I had a more of a comment and then a question based on the last response. So let me start with a question regarding the ground motions that you're producing. Obviously, one of the first things that you do is you look at the spectral shape of the ground motion and see how well does it compare to the spectral shape, the target spectral shape before you do the spectral matching. I presume you also do a series of tests on some of the key ground motion parameters like peak ground velocity, peak ground acceleration, RS intensity, and so forth. So, and obviously you have to do that for the scenario of interest. I mean, whether it's a crustal earthquake or whether you are in the stable continental region or this is a subduction earthquake. So what kind of, first of all, what kind of ground motion parameters do you constrain your ground motions to be matching or selecting the ground motions for your analysis? And regarding the question that Michael Pastor had asked, obviously, as you all know, there is a very significant, I would say, controversy regarding the undrained strength, the post-liquefaction undrained strength of cohesionless soils. There are essentially 2 versions: the constant strength or the constant strength ratio, which is the one that also was proposing. But there are some things that are more recent. So I wanted to point out that there is a work by Weber, a PhD from Berkeley, and Ray Seed and myself are looking at the sort of a multivariate regression of the case history. So all the case histories were reanalyzed, and and neither of those two are correct. So you either strength that are a function of confining stress, or a strength ratio, which is also a function of confining stress. So neither of those two approaches are entirely correct. But that's another point. That's a common part. So the question, going back to the question, is what kind of constraints did you add to your ground motions before they were selected to be spectrally matched?
Yeah, I didn't share everything of that matching, of course, but yeah, so we look at the area's intensities as well. So we use the seismic match to kind of as a tool to figure out the spectral matching, and then compare how the acceleration, velocity, and displacement and the area's intensity is changing between the original record and the matched record. What we pay attention to is the significant duration most of the time of the records. If we do a hand calc of the significant duration, that roughly what this profile is gonna see, and we try to stay in those limits. So I guess I would say significant duration would be the constraint that would kind of follow here.
Okay, thank you very much.
All right. Thank you very much, everyone. We are running out of time. I would like to thank you, Ryan and Seda, again for the presentation. Thank you also all participants for attending and for questions. I would also like to thank Ms. Elizabeth Angel from EERI and Professor Mark Veletsos from Merrimack College to help and enabling this talk series. Just to give you a heads up, the next coming talk is focused on resiliency, and we will communicate that details about that upcoming talk sometime soon with all of you. Thanks again. Wish you a very nice day.